So we're going to start chapter 9, section 3, and today we're going to talk about similar right triangles. So first thing that we're going to learn is a theorem, and this theorem states that if the altitude is drawn to the hypotenuse of a right triangle, it must be a right triangle for this theorem to work, then the two triangles formed are similar to the original triangle and to each other. So the original triangle here must be a right triangle. So the original triangle is triangle ABC. Soon as you drop in this altitude, it forms two more smaller right triangles. So I have this little one here. They can outline this one in white. So it makes this small right triangle now when I draw the altitude in there. And then I have this one over here to the right. And then I have the original large yellow one. All three of these, the white, the blue, and the yellow, are all similar triangles. So for example, if I took the first one, the yellow, and if I started it out by saying BCA is similar, and this is the yellow one, the big one, then from there I could say it's similar to the blue one, BAD, and then now finally similar to the little one, ACD. And that would have been the white one. So all of these angles are going to match. The order that you write these letters is important. On the next slide, I'm actually going to pull it apart so you can see it a little bit better. Because probably on the quiz, you're going to be asked to identify the similar triangles and write the similarity statement. Yes?
So you say the angle must not be not in the letters that you have on the angle is not.
So what you're going to look at, so B and 1 might be different, like, so angle D might be different in one of them. So I'm going to show you when I pull it apart, you'll see it a little bit clearer. Sometimes it's easier to identify the hypotenuse and write that down first, and then match all the hypotenuses. All right, let's look at the second example here. So here is my original large right triangle. So let me go ahead and, this is the original one. And I can go ahead and draw that one. So let me just redraw it here. This is the original large one, STR. Now, when I go to pull these out, I'm going to put them in the same orientation so you can see what matches easier. So next, I can pull out the medium size one, the RTU. Pull out this one. So I'm going to, again, sit the right angle in the same spot. RTU. And now I'm going to do the teeny tiny one over here. And I'll do that one in green, but I'm going to draw it in black so it shows up better. So then I'll do the smaller one, TSU. So now I've taken the large triangle, drawn down the altitude, which is the UT, which splits it into two smaller right triangles. Now I can come up with my similarity statement. So my similarity statement for the black one, I'm going to start with it. I'm going to start it with STU. So notice I put the hypotenuse there, the side across from the 90. I started with ST and then I went to the right angle. So then when I go to the red one, I'm going to do the same thing. I'm going to start with the hypotenuse, RT, and then go to the right angle. And then for the last one, do the same thing. Do that hypotenuse and go to the right angle. So you'll be expected to write a similarity statement by pulling the triangles apart. And it helps if you sit them all the same way. And maybe use the hypotenuse and the 90-degree angle as a reference.
Ms. Gordon,
Uh-huh.
how do you know if you're supposed to do RT or TR? Or SR or RS?
When you start out at the beginning, it didn't matter. So whatever you start with here, if you decided instead to start here and say TSU, then everything else has to match as well. So then the next one would have been, you would have flipped it TRU. Everything needs to match up. So if you notice on all of them, the last letter here was the right angle. The first two letters were the hypotenuses on all three triangles. All right, let's see what a geometric mean is. This is a review of Algebra 1 on the next slide. So again, we're working with a lot of square roots. So the geometric mean, you should have learned this when you covered proportions in probably elementary school or middle school when you did pre-algebra. When you solve a proportion, the cross product here is going to be when you're given two numbers, you're going to square root their product. So here we're just doing the cross products. We're multiplying x times x and then a times b. X times x gives me x squared, and then a times b is ab. So when I'm solving this proportion, I'm getting x squared is equal to a times b. Whenever I want to solve for x and it's an x squared, I need to square root both sides. So this answer is going to be x is equal to the square root of a times b. The value of x is called a geometric mean. So we're going to practice this. So you may not be given the problem in a proportion. We're going to be setting up our own proportions. But if you're ever given a question and then to find the geometric mean of two numbers, what you're going to do is take the two numbers, you're going to multiply them, and you're going to square root that product. Now, what I can do here is I could multiply 4 times 20, but I get 80. And then I got to break it back down again. So what I like to do is instead of multiplying them, do my factor tree before I multiply. And then look for the perfect squares. So here, if I factor the 4, I get 2 times 2, and then 4 times 5 for the 20, or you could do 2 times 10. I got to keep going until it's prime. So these are done. This one breaks into 2 and 2, and then the 5 just comes down. Now that I have prime numbers, I look for pairs. I've got a pair of 2s and another pair of 2s. Everything that pairs up, 1, 2 comes out of the pair. Because really what you're doing is 2 times 2 is 4, and the square root of 4 is 2. Nothing pairs with the 5, it stays underneath. Anything that comes out, you have to multiply back together. And you're done. So the geometric mean of 4 and 20 is 4 square root 5. Now, if you would have preferred to multiply 4 times 20, then you would have gotten 80. You still have to go back now and break it down. So I could have also broken this into 16 times 5 And then if you realize 16 is a perfect square, then it goes right to the answer. So it doesn't matter. Most of these problems are not going to be perfect squares, so it's easier to leave them unmultiplied and then just factor them from there. Up here, if you would have realized from the beginning that 4 was a perfect square, you could have just square rooted that and then started working on the 20. And then found the 4, found it was perfect, bring it out. So however you want to break down your radicals. Most calculators will not simplify these radicals. You will need to learn how to do them by hand. In Algebra 2, you don't use a calculator. So more than likely next year, hopefully things will be back to normal. Everyone will be in school. And for a good portion of Algebra 2, you don't use a calculator. So all of this is done by hand. All right, let's try the next one. Now, if you notice, both of these are perfect squares. You could also think of this as the square root of 9, square root of 25. Get 3 times 5, and the answer here is 15. You could have also multiplied it. 9/4 is 225. If you know your perfect squares, square root of 225 is 15. Or, let's say you didn't realize 9 and 25 were perfect squares. So then you do your factor tree. Break the 9 into 3 and 3, the 25 into 5 and 5. Soon as I have pairs, you make your pair. 3 comes out, make a pair, 5 comes out, multiply everything that comes out. You get 15 either way. So this is just a review of pre-algebra and algebra 1. Because we're going to be using it for our geometry proportions. Everybody ready? Theorem 9.7, and again, the number's not important. This is called the geometric mean or the altitude theorem. So here it says, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. The length of the altitude is the geometric mean of the lengths of the 2 segments of the hypotenuse. And I'll show you what all these words mean. So again, I have my original right triangle. Outlined it in yellow. The right angle is up here. They've drawn in the altitude. The side across from that original yellow right angle, this is the hypotenuse. So this side right here. Soon as I drew in that red altitude, I split the hypotenuse into 2 pieces. The 2 pieces are called segment 1 and segment 2. So all you did was split this hypotenuse into segment 1, segment 2, and then the way that you're going to solve for the missing sides here is you're going to use this proportion. You're going to memorize that you would put segment 1 over the altitude, which is the red line, and then the altitude over segment 2. The geometric mean is going, if the altitude is the lengths of the 2 segments. So you're going to take the 2 segments, you're going to multiply them and square root them, is basically what we're going to do here. And we're going to see how to do this all momentarily. Yes?
Will there be a case where segment 1 and segment 2 are equal?
They could be. All right, so let's see the geometric mean leg theorem. So again, we've got our original right triangle. And in a right triangle, the altitude from the right angle divides the hypotenuse into two segments, which we already saw previous. So A is segment 1, B could be segment 2. Here, the length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. I like to call this segment of the hypotenuse adjacent to the leg, I give it an acronym. I call this the SOHAL. So the segment of the hypotenuse adjacent to the leg. That's my acronym for what's going to go here. So let me show you what this means. We would have two different proportions here because remember, the C is the hypotenuse of the original triangle. X is a leg of the original yellow, and so is Y. So for my first proportion, when I want to just talk about leg X, I'm going to take the hypotenuse, which is C. I'm going to put it over the leg, and then I put the same variable, that same leg, and then its segment of the hypotenuse that it's right next to, which is adjacent to, is right here. It's A. So this segment, remember A is a segment, B is a segment, so this segment that's next to or adjacent to that leg goes in that proportion. When I want to do the other leg, which is Y, its SOHAL is going to be B. It's the segment that it's right next to. So this proportion would be the hypotenuse over the leg, and then the leg over its SOHAL. So it's the piece of the hypotenuse, the segment of the hypotenuse that's next to the leg. And these are the proportions we're going to be using. So let's try them. Everybody ready? All right, so I'm going to only do part A first. So I'm going to label my picture based on my given. So JR is 16. Is that showing up? Let me do it in black, I guess. 16. And then EJ is 9. Now up here is the right angle. So this ER here, this is the hypotenuse. And I can find it by adding 9 plus 16. The 9, this is, I could call this one segment 1. And I can say that this one's segment 2. It doesn't matter which one you label as segment 1 or segment 2. Now, to simplify my proportion, I'm going to add letters to the other sides. So I'm going to say that this side here, my altitude is going to be X. And I'm going to say this leg is Z and this leg is Y. Just to simplify my proportions. All right, so let's first find the altitude. So the proportion I'm going to be using to find the altitude is going to be segment 1 over altitude equals altitude over segment 2. So my altitude is X, segment 1 is 9, segment 2 is 16. So I'm going to do 9 over X, X over 16. I need to cross multiply. X times X gives me X squared. And again, I'm not going to multiply 9 and 16 because I'm going to factor it from here. Now, if you're good and realize 9's a perfect square, and so 16, you can just pull it out and just say x is equal to 3 times 4, and x equals 12. So my altitude is 12. Now I need to find the legs. I need to use the other proportion. So here I'm going to be using hypotenuse over leg and leg over the Sohal. You know what? I'm going to change this Y and make it blue. All right. So for this proportion, I've got to do it twice. I first have to do it for the Z using its Sohal, which is going to be the 9 segment of the hypotenuse adjacent to the leg, and then the Sohal for Y is going to be the 16. So let's go ahead and set up our proportion first for Z. So for Z, I'm doing hypotenuse, which is 25. I found that by adding 9 and 16, over Z, and then Z over its Sohal. I'm going to cross multiply. I get Z squared equals 25 times 9. Again, you can do the factor tree, or if you realize 25 is a perfect square, you could square root it, square root the 9, and now square root, and you get Z equals 15. Or actually, this was already out. Let me just do that. Square root it up here. Okay, now I have to do the same thing for Y. And I should have done that in red. Okay, but. So this was for Z, which I had written in red. Now I'm going to do Y. Hypotenuse over leg, leg over Sohal. Y squared equals 25 times 16. They're both perfect squares. I can square root them and get 5 times 4, and Y is 20. Now, if you realized that the original triangle here, let me redraw it here. And we had H, E, R. If you already found that this was 25 and you found Z to be 15, you could also do Pythagorean theorem to find this last side, which ends up being 20, if you didn't want to use the proportion. Or if you have time ever on a test or a quiz, you could go back and do Pythagorean theorem to double check your answer. So once you find two of the sides of any of these little right triangles, you could do Pythagorean theorem to find the missing third piece. So filling this in here, HJ, which was the altitude, that was 12. RE, that is, where's RE? RE was the hypotenuse, that was 25. HR, that was the Y value, that's 20. And then HE, that was Z, and that what I called Z, and that's 15. Now we're going to use the exact same picture, and we're going to do part B. And again, we're still using the proportions. Everybody ready? Now, I went ahead and I just... So if you want to just quick sketch the triangle, you can. I just duplicated the slide, so I have the same picture again. Good. Anybody else still need it? All right. Slide, and I have the same picture again. Let's try this one now. Let me label my given. They're giving me JR is 4 and JH, which is the altitude this time, is 2. And now I need to find all the missing pieces. So what I can do now, I'm still using the same proportions. What I'm going to start out by using first is the segment 1 over altitude, altitude over segment 2. So this could be my segment 2. This could be segment 1. This is altitude. Let me add in variables again just to simplify my proportions. Segment 1 I'm going to call X. This one I'm going to call Z. And this leg I'm going to call Y. You could use whatever letters you want. I'm just trying to simplify my proportions a little bit. All right, so I need to find the value of segment 1, which is EJ. So I'm going to be doing X over the altitude, which is 2. Altitude over segment 2. I now need to cross multiply and divide. So 4 times X, 2 times 2, divide by 4, X equals 1. This time it wasn't a geometric mean. It's just solving for X. So X is 1, which is EJ, which is the first thing they asked me to find. RE, that's the length of the entire hypotenuse. So I just have to add 4 plus 1, and RE is 5. Everybody good? Now that I have segment 1, segment 2, now I can do the 2 proportions for the 2 legs. So the proportions I'm going to use now are going to be hypotenuse over leg, leg over the SOHAL. So for Z, its SOHAL is going to be 1. For Y, its SOHAL is 4, because it's the segment of the hypotenuse that's next to or adjacent to that leg. So let's set up our 2 proportions. I'll do the Z first. So hypotenuse, remember we just added 4 plus 1 and we got 5 over the leg, which is Z, and then leg over the SOHAL. Cross multiply, and then square root. Z is equal to the square root of 5, and Z is HE, so that is square root 5. Now let's find RH, which is the other leg. Hypotenuse over Y, Y over its SOHAL. Cross multiply. I'm going to leave them unmultiplied because I still have to break it down. Square root. The 4 breaks into 2 times 2. I got a pair of 2's. A 2 comes out. So final answer here is Y is equal to 2 square root 5. And that is the length of RH. So that is lesson 9.3.